Today we will learn about numerical solution of ordinary differential equation. So we start with the definition of ordinary differential equation, ODE. So ODE is the differential equation that contain one or more function of one independent variable and the derivative of those functions. The term ordinary is used to contrast with the term partial differential equation, PDE, which may be with respect to more than one independent variable. So let's look at this example. This is ODE. You have two variables, y and x. Y is the dependent variable, y dependent variable, and x independent variable. This is ODE. And what is the difference between ODE and PDE? PDE have more than one independent variable. Okay, U is the dependent variable, X and T are the independent variable. So it have more than one independent variable. So in this chapter, we want to solve this ODE. Okay, solving ODE means that we want to find y. Okay, we want to solve y. And if you want to solve PDE, you want to find your u. U is the dependent variable. There are many numerical methods that exist in the area of numerical analysis, but in this section, we are only focusing on Euler's method and Runge-Kutta method. So for notation, usually the differential equation is denoted by y prime or dy dx. In this part, we also use the notation as a function in y and x. Okay, like this f x y. So this will give you the similar meaning. We start with Euler's method. This is the most basic numerical method used to solve ODE. So when you want to solve ODE, that means you want to find the approximate solution of y. Assume that we are given the IVP, initial value problem, which has a unique solution on some open interval, okay, x naught from A to B. In order to generate the numerical solution, the step size h is determined primarily with interval AB is divided into the number of subintervals n. So this procedure starts by using the initial condition. Okay, y x0, then the rest of the solutions can be generated by the iterative formula. This is the definition of Euler's method. Let H be a step size. The Euler's method for solving IVP in the interval AB can be defined as y I plus 1x is equal to yi plus hf xi yi, where yi plus 1x is a current approximate solution that we need to find. Yix is the previous solution and fxy is an evaluation of the IVP function. The values of x to be considered can be denoted by x is equal to a times h times b. Okay, this notation means that we begin with x equal to a and add up h to the value of x in every calculation of subinterval until reaching the last value at x equal to b. Okay, so this is your first value a and the last value b. This is your x. This is x0, x1, x2 until xn. Look at this example. Suppose we take 5 subintervals to solve dy dx equal to x2 minus x plus y, passing through 1, 1. Approximate y at x equal to 2. The step length h is equal to 2 minus 1 divided by 5. So h will be 0.2. X is equal to 1 times 0.2 times 2. The result of our approximation are listed in the following table. Okay, this is your first point. X0 equal to 1. X0 equal to 1. Y0 equal to 1. So 1, 1. And then this is your y prime. Y prime equal to 2. When you substitute 1 here, 1 here, 1 here, then you will get 2. Substitute x equal to 1, y equal to 1, then you get dy dx equal to 2. So this is your next x, okay, plus 0.2. So your x1 will be 1.2, x2 1.4, x3 1.6, x4 1.8, and x5 2.0. We're supposed to take 5 subintervals. So we stop at I equal to 5. Then how to find your next y? Use the formula for Euler's method. Okay, yi plus 1 is equal to yi plus h y prime I. So this is y1. y1 is equal to y0 plus h y prime 0. y0 1, h 0.2, y prime 0 2. Simplify this, then you will get 1.4. So just continue this calculation until I equal to 5. So this is your answer, 3.702336. If we take 10 subintervals, okay, so I from 0 to 10. So you just use the same formula like the previous example. But 10 subinterval, your h will be 0.1. This is your answer. This is your numerical solution of the ODE. Let's look at another example. Consider the following initial value problem. Y prime equal to x plus 5y. Y0 is equal to 1. So this means x0 equal to 0, y0 equal to 1. Solve the problem above using Euler's method with h equal to 0.1 to approximate the solution at x equal to 1 in tabular form. And then find the percentage of relative error of exact and approximate y for A and sketch the graph. Let's complete the result in the table form. This is your x. So I 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. X0 equal to 0. Y0 equal to 1. And then this value y prime 0 is equal to x0 plus 5 y0. 0 plus 5 times 1. So you will get 5. Okay, that's how you get this 5. And then how to get the next y here. Y1 is equal to y0 plus h y prime 0. Okay, y0 is equal to 1. H is equal to 0.1 and y prime 0 is equal to 5. So 1 plus 0.5, so you get 1.5. So that's how you get this value. Just calculate it until 10 subinterval. This is your approximate solution of y, 59.73. Now look at this exercise. So we have 3 questions for Euler's method. Question number 1. Consider the initial value problem y prime is equal to 3 over x plus y with y1 is equal to negative 1. Use Euler method with step size 0.5 to approximate solution at point x equal to 2. This is the ODE. This is the initial value problem. This is the given h. So you want to find the solution at x equal to 2. Let's write down the values in the table form. I0, 1, 2, x, 1, 1.5, 2, and then y, I, negative 1, 0, and 1. And y prime I, 2, and 2. Okay, so I have write down how I get all these values. So yx at x equal to 2 is equal to 1. And then question B, use the improved Euler method with step size 0.5 to approximate the solution yx at x equal to 1.5. So 1.5, x equal to 1.5, the answer will be 0. Question number 2, use Euler's method to approximate this ODE at points x equal to 0.1 and 0.2 with h equal to 0.1. Similarly, this is your h, this is your initial value problem, and this is your ODE. Write down in the table form 0, 0.1, 0.2, and then find the solution of approximate y when x equal to 0.1 and x equal to 0.2. So the answer will be 1.1 and 1.22. Question number 3. Similarly, this is your ODE, your IVP, approximate value of y for t equal to 0 times 0.2 times 2. Okay, give your answer accurate to 6 decimal places. This is your ODE. This is your t. Okay, so from this you know that A is equal to 0, B is equal to 2, and H is equal to 0.2. So just use the same calculation like the previous one. Then you get this answer, 0.053993. Next method will be the fourth order Runge-Kutta method. The Runge-Kutta method is more accurate compared to Euler's method. Okay, as usual, given y prime equal to fxy and the initial condition x0, y0, and we want to find the value of y at other values of x. In this method, we need to calculate 4 intermediate values as follows. We need to find your K1, K2, K3 and K4. Where H is equal to Xi plus 1 minus Xi, and your next Y, Yi plus 1 is equal to Yi plus 1 over 6 times K1 plus 2, K2 plus 2, K3 plus K4. Now let's look at this example. Given dy dx is equal to x2 minus x plus y, passing through 1, 1. Approximate the value of y for x is equal to 1 times 0.5 times 2. So y0, x0 is equal to 1, 1. And h is equal to 0.5. This is your starting point. A equal to 1 and B equal to 2. You need to calculate the 4 intermediate values of K1, K2, K3 and K4. Okay, K1, K2, K3 and K4. K1 H F X0 Y0. This is your H, X0 Y0 1, 1. Okay, so just substitute X0 equal to 1, Y0 equal to 1 into your dy dx. Then you will get 1. Okay, for K2, H times F, X0 plus H over 2, Y0 plus K1 over 2. Okay, this is the calculation. Simplify this, then you will get this value. This is K3 and K4. After you get all the K1, K2, K3 and K4, substitute into your formula for next value of y. So y1 will be this value, 2.249349. So this is the value of y1 at x1 equal to 1.5. To compute y at x2 equal to 2, we repeat our previous calculation, but now using this value, x1, y1. Just now we use x0, y0, right? So now we will use this value, x1, y1. So we need to find K1, K2, K3 and also K4. After that, you need to substitute into your formula, y2. So y2 will be 3.998276. So this is your y2 when x2 equal to 2. So see the following table for the result of our calculation. So this is the initial condition that given in the question. This is all the value that we calculate just now. Okay, then this is your answer. When x equal to 2, this is your approximate solution for y. If we take 5 subintervals, we have y approximate 3.999948 at x equal to 2. If we continue by taking 10 subintervals, we obtain 3.99997 at x equal to 2. So we can conclude that if we increase the number of subintervals with smaller value of h, then we obtain a more accurate approximation. I leave this exercise for you. You can check the solution. Okay, so that's all for today. Thank you.